So this week, I'm very pleased to introduce Dean Karlen. So I should say, as by way of introduction, we often tell our students that an education in physics is all about general approaches to problem solving. And that actually has applications well beyond what seems like physics. So there are lots of examples of physicists applying their sort of physics problem solving expertise to things that are, you know, real world problems. And I think Dean's example is a great example of that. So he's a particle physicist, high energy physicist by training, particularly laterally working on neutrino physics, but developing experiments. And he's worked on many previous particle physics experiments, been very, very prominent in that field. But I guess when the pandemic hit, he decided to put his energy towards modeling the pandemic. And it's not that he's an epidemiologist and an expert on the whole topic, but he brings some new insights from physics into the mix. And so he's spent the last year and a bit modeling the COVID pandemic, and that's what he's going to talk to us about today. So thanks, Dean. It's all yours.
Great. Well, thank you very much, Douglas, for that nice introduction. So in this next 45 minutes or so, I hope you'll learn something about how a physicist approaches a problem in epidemiology. I'll summarize some basic aspects of epidemics, talking about a rather simple model and a simplified explanation of that model. I'll then use that model to interpret data from BC, but also elsewhere in the world, breaking it up into 4 different segments. First, before we had the variants and vaccination that were playing a big role in the spread of COVID-19. But then we had the first variant of concern, the variant now called Alpha from the UK. So we'll look at that. Then seeing the effect of ramping up immunity thanks to vaccinations. And then to finish off, looking at the most recent variant of concern, so-called Delta variant. So just the fine print here is that this is a presentation from a physicist, so not having a full background in epidemiology, but what I'll be showing you is work that's come about through interactions with global epidemiological community, in particular, this group called the BC COVID-19 Modeling Group. There's the website where we're now posting reports every 2 weeks about the situation in BC. So I thank the members and the organizers of the BC COVID-19 Modeling Group for their efforts and also their patience in dealing with people like myself from outside of the community. So one of the most important basic features of epidemics, of course, is the rapidity in which they spread. Here's a naive picture of a spreading epidemic where you've got this population of happy people and one person who is infected. And that person then contacts one of the uninfected, the susceptible person, and infects that person. So the next step is that those 2 people contact susceptible people, and then we're gone up to 4 infections, and then from those 4 we go to 8 infections, and from 8 we go to 16 infections. So we could just keep going this way, but the remarkable thing is we only need about 30 more steps, and we've gotten to the whole population of the Earth, 8 billion people. It does not take that many steps in this little animation to get to a very large number. In their normal experiences, we're often exposed to systems that are growing linearly. In this case, you go from 1 to 2 to 3 to 4 to 5. It takes you 8 billion steps to get to 8 billion. Each step is increasing by the same amount. Epidemics aren't going in that fashion. So that previous example was 1 to 2 to 4 to 8 to 16, the growth in any step depends on the size of the previous step. So in this very simple exponential growth, we had the number of cases or individuals infected was 2 to the n, where n is a step number. So in infections, the new infections, the number of new infections in any day is proportional to the number of people infected at that time. So it follows this kind of scheme where the growth depends on the size at a particular time. So our infections grow exponentially or decline exponentially. And so to start building up a model following this approach, we need to bring in a little bit of realism. Clearly not every day does a contagious person infect exactly one person each day. So instead of that, we introduce an adjustable parameter. I use the symbol alpha, being the average number of people a contagious person infects per day. And you could call that alpha a transmission rate. So given alpha, and if you knew how many contagious people there are on a particular day, then the number of newly infected people that day would just be delta I, the product of alpha, the transmission rate, and the number of contagious people. So you can see what happens when we let this epidemic propagate. We start with C contagious people. The next day, we have C plus the new infected people. If those people become contagious immediately, then this is the number of contagious people we have. And then the following day, you have continued growth on this way, and effectively you just have, after n days, the original number of contagious people plus 1 plus, or multiplied by 1 plus alpha to the nth power. And when we show that kind of growth, we're familiar with the exponential curve. It's a very worrying curve. Often we'll be showing the data in a log scale, a log plot, and an exponential growth appears as a straight line on those plots. So we need to introduce more realism into this model, not just this transmission, but also include immunity, both from natural cases. So when you are infected, you gain natural immunity, or if you're vaccinated, you gain vaccination immunity. So suppose that same person and that same epidemic, that person is now roaming in a population that's 50% immune, then on average, that person's not going to infect alpha individuals because half of them are immune. They will only infect 1/2 alpha. So this is the typical approach in these models, is to say that the newly infected number will not be alpha times C, but alpha times the susceptible fraction, the fraction of people who are susceptible times the total number of contagious people will tell us how many newly infected there are. So when we're in a situation where this susceptible fraction is rapidly falling, as it is the situation right now, we start to see the epidemic spread no longer being simply exponential. It's no longer following that pattern that we saw before. So that's one extra effect. The other one being the fact that contagious people have a limited time to infect others, say some time t. At some point, the contagious person stops because they either recover, or perhaps their symptoms are followed by a positive test and they go into quarantine so they don't infect others that way. So when we include this effect, and if we have a relatively constant transmission rate and a constant susceptible fraction, then the steady state solution for this circumstance is still exponential. But the the growth factor for that exponential is no longer simply alpha. It depends on this length of time t. So we can just consider it as another quantity. I call it delta. This is the fractional growth rate per day. So that number can either be positive, it can be 0. If it's 0, that means that there's no growth. It's a steady number of contagious people, or it can be negative, so that the number of contagious individuals is dropping. So you've heard the term flattening the curve. What does that mean? It just means we want to first get any kind of growth in contagious individuals, a positive growth to at least 0 and then to negative. So how do you do that? Well, you consider the fact that there's a source of contagious individuals, this alpha times S over N times C, that's the new contagious people. But there's also a drain if as contagious people are removed. So we can think of this as a contagious pool, that we want to drain that pool faster than it's being filled. It's being filled by transmission to new individuals, but it's being drained as well. So if we want to get this growth negative and as negative as possible, then let's speed up the draining. That means reducing the amount of time that an individual circulates in the community, possibly spreading the disease. So having quick results from testing and going into immediate quarantine after a positive test reduces that time. Also, the idea of contact tracing and testing removes contagious people from the pool more quickly. And of course, we can also slow down the filling by slowing down the transmission rate. Do that by reducing social contacts, staying apart from each other, wearing masks, but also reducing the susceptible population. We can reduce the number of new infected people by reducing this factor. And so vaccine immunization is playing a big role in doing that. So to understand if we're in growth or steady size or in a decline, we want to track the epidemic with data. It's not practical to directly count all contagious people, not a mechanism or a practical mechanism to do that. So instead we count people who perhaps developed symptoms and got a test and came back positive. That's one count. We can count people who had more serious symptoms and needed admission to hospital, and also counting people who succumbed to the disease. And there's many sources of these data. There's lots of challenges in using these data, large variability from day to day, much of that due to the reporting process. And as well as these data tend to reflect the state of the epidemic with a delay, a week ago or more. So by using models, we can simplify the characterization or the tracking of this epidemic with a few simple parameters. And this sort of consolidates all of this complicated data into a few numbers rather than entire history of cases or hospitalizations or deaths. And so I just illustrate a model that allows this to happen on this slide here, where this model and other models simply mimic this propagation between different population categories. So, for example, we have that contagious population. Those people can get symptomatic and then maybe get a positive test and then be reported. They may go into a hospital, and then we increase the number of people that are hospitalized. So we just have these different categories in these blocks. And for some of these blocks, there's data that exists, a time series for data for these various quantities. And so we can adjust any parameters in our model, such as that transmission rate, in order to improve agreement between the model and these categories for which are our data. and therefore have a model that has some connection, some abstraction of reality that does allow some degree of forecasting, or at least basic understanding of how things are related. So let's apply this first to the situation where we didn't have variants of concern or vaccination playing a big role. This was up until about February or January of this year in BC. So this is the pre-variant of concern and vaccination era. So in that era, in BC, this is before mid-February or late February, we saw infections growing or declining exponentially over different phases. And these changes in exponential growth rate were attributed to changes in behavior. And given that human behavior is to a great extent unpredictable, this means that predicting changes to growth rates was difficult to do in any accurate way. So we did see transitions in growth rate that were a direct consequence of new health measures brought in by BC in March of 2020, just as the epidemic was starting. That changed the growth rate dramatically, but also in November when after some period of a long extended growth, new measures came in and we saw that growth decline. So the interesting thing, though, is in BC and in most jurisdictions, we see long periods of roughly constant growth rate. And that does give us some forecasting ability. So in summary, we have, during this phase, we have rather simple exponential behavior, but the transitions from one phase to another are unpredictable. So just as an illustration for that period from July to February of this year, this is the cases per day, the little dots, and the big stars are just to help your eye to see the weekly average, again being cases per day. So on the right is the linear scale, and on the right is log scale. And remember, for log scale, exponential growth appears as straight lines. So we could simplify the description of that time series of data with a model saying that we had constant transmission rate in this period. Then after August 28th, we had lower growth, and then return to rapid growth. And then on November 10, on or about November 10, we had a new health measures bring down that growth rate. So it is very useful to be able to simplify this time history into these blocks of periods, or blocks of time for which there was a constant transmission rate. And to illustrate that further, just to show, this is that delta, the daily growth. We're experiencing 3%, then near zero, then 5% per day growth, and then a decline of about 0.5% per day. So that's the kind of range of growth that we experienced here, and also in many US states and in Germany, somewhere between plus and minus 5% a day, except at the March of 2020, we saw 20 or 30% a day before any lockdown started. Now, interestingly enough, not all epidemiologists followed that kind of an approach. For example, our BC epidemiologists at BC CDC characterized the spread of COVID by a daily changing growth rate, effectively. So this makes it much more difficult to relate periods from one period to another, or to make predictions or forecasts. And just to overlay on top of their curve, I show a summary of just these daily growth rates being negative here, then being a positive, close to zero, then quite large, 5%, then again, slightly declining. So not only do we need to model the general behavior that we've seen in data, in any data analysis, you also need to understand and model that sort of variation that's outside of the control of the experimenter. And so this is an aspect of the model that's being used here to characterize the BC data. So here's that representation of the epidemic in BC over that period before the variance of concern. And then this is simulated data that represents the same similar variation that we see from day to day. And the interesting thing is that this is also another simulation of the same circumstance. You can have situations in epidemics where early on in the epidemic, you have more than the expected number of infections, and that affects all future observations. So it's not like each day's observation is independent of one another. It's been very useful to be also looking outside of BC to learn from what has happened in other jurisdictions, because it may happen in BC as well. So particularly with the United States, I've been engaged there looking at modeling each of the US states. And there's actually a large effort along those ways with 40 or 50 teams submitting each week a 4-week forecast to the US CDC Forecast Hub, forecasts of cases, hospitalizations, and deaths. And the median of those forecasts are being used for their official forecasts. And so just to give you a feeling for the kind of data one was dealing with, again, you're seeing periods, and here's Wisconsin from March until February, broken up into periods, again, of constant transmission rate. You can see that hospitalization and deaths follow curves that are generally just derived from how cases change, and they generally follow the expectation just by using cases alone to characterize the spread of the disease. This is a curve derived for how many people are in hospital, and the data remarkably follows quite well. California, just another state. You don't see perfect agreement by any means, but there's some correspondence with during a growth in cases, you're seeing the same growth in hospitalization and in deaths with a bit of a lag. And all of that can be found, results from those teams are posted each week, and you can compare it to previous data to compare different models. So there's quite a lot to be learned from that exercise. I think it's clear now that case data has provided the best information for us to understand how COVID has been spreading. Of all of the various data sources, case data being the most powerful. This idea to use long periods of constant transmission rate has been a good approach. It is the only basis for making any kind of extrapolation or forecasting. There's been many other attempts by other groups, actually rather large groups like Google AI and Microsoft and Facebook AI, putting together just as much data as you could, phone mobility, insurance information, weather, working at a county level, not the state level, using machine learning methods. Interestingly enough, none of those have really delivered significantly better or even as good forecasting performance as a simpler model that uses just case data. And likewise, it's interesting that one does not have to have very complicated age-structured models to predict future hospitalization or deaths. So let's turn our attention now to variants of concern. After this period of several months coming up to the end of 2020, had a general idea how how to characterize the spread of COVID, but things got quite interesting in December of 2020 and in January, when in the United Kingdom, just shortly after them relaxing their health measures in early December, they started to see rapid growth. But that rapid growth had much to do with the fact that a new strain of COVID was spreading rapidly in the UK. It turned out that their standard test protocol, their PCR test, targeted 3 genes to identify whether or not a person was infected with SARS-CoV-2. And interestingly enough, out of the 3 genes, just one of the genes was not present in these individuals being tested. It's called the S gene. So those cases were referred to this 4-letter acronym SGTF, S gene target failure. So the other 2 genes were seen, but the target S gene was not seen. And since this was a test being performed on all individuals, it was a remarkable and fortuitous indicator to identify this very first variant of concern. In almost real time, one could see the growth of that variant of concern. And we see over on the right here in light purple are the cases that had the S gene, and in the dark purple, those cases, weekly cases that did not have the S gene, and you see a rapid rise in the SGTF cases. So a nice thing about the Public Health England is that they issue these reports on a regular basis, but they also make this raw data available for analysis. So it's just counts, it's numbers per week. But reading them off of a plot like this would be very challenging. Having that data allows us to do more sophisticated analysis, which is what we did. There were many ways to analyze that data, but it turned out the most powerful way is the most simplest way. So if we just consider that there were 2 independent strains propagating in England at the time, call one a variant and a non-variant. The only difference being that they had a different exponential growth rate. Then if we just look at the ratio of the number of cases, and we had that raw data available, so we could do this, we would also see that ratio grow exponentially, and the growth rate coefficient, S here, is called the selection coefficient in population modeling. So we're measuring effectively the advantage of one strain over the other by just looking at the ratio of the number of cases each week. So here instead of having an arbitrary amplitude in front, I've just said, okay, well, why don't we reference the time to the day T0 where that ratio is 1. So that's the day that the variant becomes dominant. It has the same number of cases as the next day and then as the other variant. And then future times it will have more cases. So that data was fit thanks to the fact that the UK makes this data publicly available. And all of those different regions are shown on the right here. I've scaled by a factor of 10 each region so that we can see them individually. And these are days before becoming dominant and days after. And prior to B117 coming into existence, in the UK, there was a few percent of individuals, or sorry, a few percent of cases that did not have that S gene, but they weren't B117. They were just a mutation that didn't have the S gene. But then you see the SGTF growing rapidly, and each dashed line is a factor 10 here. So it went from that background rate of a few percent of cases growing to dominance. And the interesting thing is, shortly after becoming dominant, its advantage declined significantly. And that dominance occurred around the time that new measures were brought in. So we saw this variant B117 having an enormous advantage of about 14% a day prior to the lockdown, and then about 7% a day after. So seeing this go through the UK gave us the information of how to deal with such a situation in other jurisdictions as it comes through. And so, for example, in the United States, we also had public data, but this time being provided by a private company for several states. Again, looking at that ratio of S gene target failures to non-S gene target failures. So back in March 16, I gave a presentation to the US CDC group to show them, okay, we have this data, and now we can predict the consequence of B117 because this data is made publicly available. So we were seeing here the growth advantage being about 8% in the US. And so this was a relatively highly vaccinated population. So we're not seeing the 14% that UK saw before their lockdown. We're seeing numbers closer to after their lockdown of about 7 or 8%. Now, just as a couple examples of Florida and Michigan, take a look at those two states. Can we forecast what's going to happen to those? And that was the purpose of this presentation. So up until this point, this was the data that we had up until March 16. And the genomic data told us that we had about 60% or so of cases were from the variant. So this is one of these is Florida. Here's Florida. So if we projected forward to that date, we were a little bit beyond dominance. So we didn't have this curve here. We just had the case data. We're at this point where people were talking about a plateauing in the US, that it wasn't declining as fast as before. People are getting more complacent or something. But no, this plateauing can be attributed just to the growth of B117. We didn't have any data that was specifically here. We had from helix.com just a random sampling of cases and that ratio showing us what was going on. So we could make a future projection that this plateau was not going to just flatten out, or it wasn't going to decline. But if people were behaving the same this whole period, we'd expect the cases to ramp up just because B117 is becoming more and more dominant. So this day we had, the original strain declining at 4% a day, but B117 was increasing at 3% a day. It had an advantage of 7% a day. And so that was a prediction for Florida, but Michigan was a stark prediction at that time. There was growth there, but the growth was around 4% a day. If it was just due to the fact that people were relaxing and so there's a higher transmission rate, the vaccination was going to turn this thing over. But in fact, knowing the genomic data, we were seeing 4% growth a day because the original was about 0% a day and the B117 was about 8% a day. And since they were about 50-50, that meant we were seeing 4%, but that 4% was going to turn to 5%, to 6%, to 7%. So faster than exponential growth due to the fact that B117 was coming in. So with hindsight, we can take a look to see whether or not these predictions did come through. I gave a follow-up presentation a month later showing that, in fact, well, there was the data we had till March 14. There was our March 16 fit with the green, and the red dots are the new data that came in the 5 weeks following that forecast. So in fact, it did sort of follow what we expected, and notably Michigan as well. It was quite frustrating seeing this new data come in following exactly this forecast and nothing happening in Michigan. Something happened, still don't know what, to turn that around. but that could have been turned around a lot sooner. So of course, all of these forecasts weren't great. Here's Utah predicted a slight rise. We didn't have genomic data, so it was just simply based on how much this was flattening out. So it was prone to error. Here in BC, though, unfortunately, VOC information, our genomic data, was not being provided in a public way. We were getting anecdotal information every once in a while. We would hear how many new variants of concern were identified, but we were flying blindly. I was looking back at a presentation in February of this year. We had no VOC information in BC. Gave this presentation showing what might happen. So back then, we were declining at 0.5% per day, this slow decline, and over a long period of time, you'd expect that the cases to continue to decline. But what would happen if there was a variant of concern, a B117 in BC? This was just hypothetical. If we started at 0.5% in January 1 or some larger number on February 1, how does it grow? Well, the cases would grow, of course, quite rapidly. This is under the assumption of about 6.5% advantage for the new strain. So these number of infections of the new strain, these are the declining infections of the original strain. This is the total number of cases in green. This is the number of cases of the variant, presuming that, well, we're not going to catch all of them. They're going to only do identification of some fraction, and it's going to take some time for the genomic data. So it comes in late, but we can see this growth here ramping up before you see it in the cases. And so I guess the scorecard here for this is, well, I got 1 out of 2 right. I predicted that there would be a way to identify in BC the variants, but I also thought that that data would be made public, and I was wrong about that. So we didn't have access to that data. So we couldn't see this thing coming. In that same presentation, I said, well, obviously we're not just, no government will just let that growth go forever. Somehow, some kind of lockdown would have to occur. I suggested maybe the beginning of April. Remarkable guess, given that on March 30th, there was a lockdown. But I thought that would have happened earlier in this rise because of the fact that we'd have this genomic data and we'd be able to predict, just like Michigan or Florida. So unfortunately, my scorecard's pretty poor again. So I did predict, remarkably, a lockdown in early April, back in early February. But I predicted that it wouldn't be, we wouldn't have a huge jump in cases because effectively we'd be seeing it coming. So in fact, our daily cases went above 1,200 before it turned around. But I also made a mistake thinking that we weren't going to be successful, in that we had this rapidly growing B117. In the past, we've been able to turn down the growth rate by about 5% a day. So that would leave us still growing. But I did say this wasn't a forecast, so I'm not too disappointed they weren't right. But if we take a look at how things turned out, first of all, our BC modeling group report did give, start making reports every 2 weeks about the current situation in BC. So I encourage you to take a look at those if you're interested in it going forward. Back in mid-April, we did know that new lockdown at the end of March occurred. It was called the circuit breaker. And we did see already by the 11th of April, a decline in cases, that we weren't going up that exponential. But which of these curves was not sure. These were just possible scenarios given our belief on how much you could really turn that situation around. So if we take a look at our next report on April 30th, we had that extra 2 weeks of data. And in fact, we found that did turn over. That was great to see. So we had a larger effect than we expected from the circuit breaker. So we also had made several projections going from there for each of the health regions in BC. And here's this 5 health regions in BC as a whole that April 30th forecast is shown. And then in red, we're just showing the actual data that came in. So it was pretty much consistent with these bands that were meant to represent about a 68% interval. But here's what transpired during that during that period. So we saw that the circuit breaker was sufficient to reverse the growth due to the alpha and also the gamma variant. By seeing the data that BC finally released, here is that ratio that I was showing you before from the US and from UK. For the BC data, we see that the VOC cases having a strong advantage until that lockdown. That advantage then declined to 4%. And thanks to that, that tells us why we saw the overall decline. So it's interesting that these lockdowns seem to have had a greater effect on the variants of concern than on the original strains. And that helped turn the situation around. So the next few minutes, I'll talk about the vaccination phase and then move on to the latest variant of concern. So the vaccination modeling, I mentioned earlier on that we already include that in models even early in the infection, in the epidemic. The susceptible fraction plays a role in how many new infections there are. So we just need to know the rate of vaccination and how immunity grows with time after being vaccinated. And data from Israel turned out to be very useful to tune the models, because they, in an early phase in February, they were already having large fractions of age groups being vaccinated. And so this is their case history modeled by the same model. And then seeing that over this entire period of time, we could describe the spread of COVID with a single transmission rate, constant non-pharmaceutical interventions, just by including vaccination. And that turnover that we see here fits nicely, telling us something about how the efficacy grows with time. It takes some time for that to grow. We saw this also in the phase 3 trials, and this kind of growth was consistent with what we saw in the phase 3 trials. So we apply that model with the vaccination to the more recent data. This is our report from a month ago, where we were in the circuit breaker. We were seeing the data cases decline exponentially. It was nice, but we also knew that coming up, the government was considering to relax the circuit breaker. And this was the projection of what happens when we see that relaxation. Sometime after, our projection was that it would grow and then decline. And the reason for that is shown on this next slide, a little bit of detailed information, where we're seeing in the blue curve the susceptible fraction declining as we're getting more and more vaccinated. That's this curve. The growth rate depends on the product of that transmission rate and that susceptible fraction. So the transmission rate was quite high and producing large growth of the variant. So I'm just showing for the variant here. We're seeing the variant rapidly grow in daily cases. If we take that alpha times S over N, we get this number here. Compare it to these 3 values. The solid line here is that product that gives us 0 growth, and the dotted is 2%. So we're at like 8% here. So the lockdown came in. that brought us down to a point where alpha was close to zero growth. But actually, when we multiply by S over N in this blue curve, we're seeing that goes into great decline. So it was coming, we're in the middle of May and deciding, well, what's going to happen when this gets relaxed again? Well, under the assumption that the transmission rate after relaxation goes directly back to where we were before, we would see that product no longer having large growth, but only having about 2% growth, and then weeks later being declining again. So that's why you see a bit of growth and then a decline. But in the case of this dash case was a less optimistic vaccination schedule. But in fact, we've gone even better than the blue curve. So it turns out that that forecast was actually not that great of a forecast. We saw that the cases are continuing to decline. I'm happy to have that forecast be not fully predictive. It'll be interesting to figure out what happened, but our cases have not returned to a growth period. And we'll see if it happens in the next few weeks. But that's great news to see that. In fact, this is the projection if there was no relaxation at the May 25th. And the cases are actually coming down slightly below the mean expectation there. So just to look at how immunization is being seen in other places in the US, here's Florida. So we looked at Florida and the variant coming up, and then something happened to turn that around. Again, do not know. Then we saw this decline, and it's declining faster than exponential thanks to vaccination. Likewise, Michigan, this is a remarkable curve. Here from January to now, we have one transmission rate, one transition here to a lower transmission rate, all fit really remarkably closely to this case data with very few parameters. Again, this rapidly growing, rapid drop is due to immunization. The actual growth rate seen now in the US in the different states is predominantly dictated by the susceptible fraction in that state. There's quite a wide distribution of immunity in the US states. So these blue dots each represent one state. You can see in some states the susceptible fraction is only 30%, as other states is 55%. This state, by the way, is Puerto Rico here. So you can compare that to Canada. We're not quite at their level of susceptible fraction because they got immunized much earlier than us. Here's Germany. But also you see there's a much smaller distribution or narrower distribution. The next slide actually shows what's happening in growth rate as a history from January to now. You see the growth due to the variance, a decline after turning it around, and now you see just a nice steady decline in growth as the susceptible fraction gets lower and lower. So here on the right is just the last 30 days, seeing the susceptible fraction decline at the same time the daily growth rate decline. So in the last couple minutes here, just taking a look at the latest variant of concern, the Delta variant. Again, the UK has led the way in terms of being hit by another variant of concern. They're first to see this and document this well. And again, that same rapid indicator that they had used before is useful again. Here is the situation going into December where the dark purple is the growth in SGTF, and then it was pretty much all cases, almost 100%. Now you see a decline in cases due to that have SGTF because the variant does not have SGTF. So they can continue, and they have been continuing doing this PCR test. And they've been continuing to make their data publicly available so we can do more sophisticated analyses to understand what growth advantage that corresponds to. And also in, again, the US states make their data publicly available for some states to measure both the growth of the gamma variant, but more concerningly, the delta variant in teal color here. In each of the states, you see the delta variant having a greater advantage compared to the P1 does not have as great an advantage. And here we're measuring the advantage with respect to the alpha strain, so the dominant strain. So something between maybe 5 and 9% per day is the advantage for this Delta variant compared to B117. So that could be a serious circumstance. And in our last report, just as an illustration for a particular choice of prevalence in early June, how these different advantages could affect our future cases. But this is in a circumstance where we thought there was going to be a slight growth in the alpha. In fact, the alpha continues to decline. So likewise, these different scenarios for the delta will be lower, which is great news as well. But we're still in a situation where there's a great deal of uncertainty, where we don't have great genomic data from BC made publicly available. And we don't therefore know its current prevalence well or its growth advantage here in BC. We hope that we will get the screening data in the future. We can start to see the effect of the delta in that screening data. This is the data I showed you before. You might notice that these last points are starting to drop. So just like in the UK, seeing a drop in a screening test, here is the fit to that data when we include the delta. So we can start measuring how strong the delta is in our data. So that brings me to the end. It looks like I went a few minutes over time, sorry for that. But I guess just in summary, I encourage you to take a long view if you're trying to make sense of the COVID-19 data. We see lots of daily variations, but when you look at weekly averages, the trends tend to last for months at a time. That is, we see constant transmission for 1 or 2 months or 3 months, and then we see this transitions between those periods. The variants of concern continue to be of concern. The rapid screening data is very useful if made public. We still need to track this in BC to understand how things are going to transpire in the next weeks and months. But vaccination clearly is helping keep VOC under control in places around the world, such as BC, where we're fortunate to have such vaccines. If we want to have further relaxation of measures, we'll want to further reduce the susceptible fraction. And that means we need to have as many people vaccinated as possible. So please register to get vaccinated if you have not already done so. And just a final plug, if you wish to follow our work within the BC COVID-19 modeling group, encourage you to see and go to this site where we have every 2 weeks posting a report and a short video presentation summarizing that report. So again, thank you for your attention, and I'm happy to answer any questions you may have. Thanks, Doug.
Great. Thanks, Dean.